Hello once again, dear students. Welcome to our fourth lecture on ancient or prehistoric mathematics. Last time, we focused our attention to Egyptian mathematics, particularly their system of writing and their arithmetic. So for this session, we shall look into Babylonian mathematics and the Rhind mathematical papyrus. So what are the objectives set for you for this session? At the end of the lesson, you should be able to describe the Babylonian number system. Number 2, convert Babylonian cuneiform to our current day numbers and vice versa. And number 3, perform operations on Egyptian hieroglyphs. And when we shall get into the second part, which is the Rhind mathematical papyrus, I will be expecting you to be able to describe the Rhind mathematical papyrus and solve problems or specified problems or selected problems from the RMP or the Rhind mathematical papyrus. Okay, now we proceed to the first slide. Aside from the Egyptians, the Babylonians marked great influence on the development of mathematics. In fact, the term Babylonian is used to refer to those who occupy the alluvial plain between the twin rivers. Can you remember the twin rivers in your history? Okay, the Tigris and the Euphrates. Yes. And the land between the rivers, the Greeks call it Mesopotamia. The land, Mesopotamia means land between the rivers. Most of it today is part of the modern state of Iraq. Okay? Although both the Tigris and the Euphrates rise in Turkey. Now, shortly after the 3000 BC, the Babylonians have developed a system of writing from pictures, pictographs. Okay? Whereas the Egyptians made use of pen and ink to keep their records, the Babylonians used first a reed and later a stylus. Then the end is triangular. So with this, they made impressions, okay, in moist clay. So their writing material is a clay, moist clay. Now clay dries quickly, so documents had to be relatively short and written all at one time. But they were virtually indestructible when baked hard in an oven or by the heat of the sun. Now, in the Babylonian number system, a vertical wedge, vertical. You know how a wedge looks like, this vertical wedge. This one, vertical wedge. Okay, this is a vertical wedge. A vertical wedge represented 1. So this one represents 1. While a horizontal wedge, okay, a horizontal wedge represented, okay, 10. So that's the difference. Can you recall from the Egyptian hieroglyphics? 1 is represented by a vertical stroke, and 10 is represented by a heel bone. Yes? Okay, so for the Babylonian system, 1 is represented by the vertical wedge, and 10 is represented by horizontal wedge. So the numbers 1 to 59 then are written in this manner. Okay? So your 1, 2, 3, 4, 5, 6, 7, 8, 9. Take note that they are written in rows of 3. If it exceeded 3, okay, we have to write the next number below. Look at how 4 is written. How many vertical wedges? 4 vertical wedges. But the first row contains 3. And the remaining wedge under, it's written under. Look at 5. Look at how 5 is written. Let me just magnify. If we could magnify and think we cannot magnify anymore. Okay, so let me just write then. So your 4 would be written in this manner. Okay, 1, 2, 3, and then 1 below. So that's the way 4 is written. This one corresponds to number 4. Looking at number 5, just the same. The first row consists of 3 vertical wedges, and the remaining two are written just below. Okay, so this is how 5 is written in the Babylonian cuneiform. So the remaining or the succeeding numbers are then written in this manner. Look at your number 6. So number 6 consists of two rows of 3 wedges, vertical wedges. 7, 2 rows of 3 vertical wedges and a row with 1. And 8, 2 rows with 3 vertical wedges and the third row having 2. And 9, look at how 9 is written, 3 rows of 3 vertical wedges. Now when we reach 10, then we have to make use of the horizontal wedge. So your 10 looks like this. Okay, a horizontal wedge. So this one represents 10. How about the next numbers? The next numbers will be represented by 11. Look at how 11 is represented. It will be a wedge, horizontal wedge for 10 and a vertical wedge for 1 to make it 11. Next, 12, 13, 14. How about 20? So how about 20? It will now be represented by 2 horizontal wedges. Okay? In like manner, 21 will be 2 horizontal wedges and 1 vertical until 29, which is represented by 2 horizontal wedges and 9, okay, 9 vertical wedges. And when it comes to 30, 3 horizontal wedges. Next, until number 59 only. Why? Okay, until number 59, which consists of 4 or 5 horizontal wedges and 9 vertical, okay, vertical wedges. Why? Why is it that we can use it until number 59 only? Because your Babylonian cuneiform, okay, is a sexagesimal system. It makes use of base 60. Okay, so please take note of that. This is sexagesimal. Okay, we proceed to the next. So, how do we then represent a number? Okay, because that's the next question. Okay, that's the next question. How would I represent now a number greater than 59? Now, let's look at example number 1. Looking at example number 1, okay, I'm looking at this, 21. Okay, now, 1 here, 1, let me underline, is for 60 raised to 0. And the 2 horizontal wedges here for 60 raised to 1. So if we convert this into our current day number, then it will be 1 vertical wedge is 1 times 1, because 60 raised to 0, 60 raised to 0 is equal to 1. Next, how about the 2 horizontal wedges? The 2 horizontal wedges is equal to 20. Multiply it to the next, okay? Multiply it to the next power of 60, which is 60 raised to 1. Therefore, this number is equal to, in our current number system, this is equal to 1,201. Moving on to example number 2, we have from the rightmost rather, 2 horizontal wedges, 5 horizontal and 2 vertical, 2 horizontal and 8 vertical, and then 1. Okay, and then 1. This stands for 20. Yes, 20. Okay, this one stands for 1. How many horizontal wedges do we have? 1, 2, 3, 4, 5 plus 2, 52. And the next set, we have 2 horizontal and 8 vertical. What is this equal to? 28. And lastly, we have here. Okay, so this will be multiplied to the following powers of 60. This is for 60 raised to 0, which is equal to 1. Then for 60 raised to 1. Then this is for 60 raised to 2. And then this is for 60 raised to the third power. Okay, so now, let's look into this. Now we have 1 times 60 to the third plus 28 times 60 squared plus 52 times 60 plus 20 times 1, which is equal to 319,904. Okay, now, how about the other way? We are given a number in our current system and convert it or express it in the Babylonian cuneiform. For instance, 1,000. How shall we express 1,000 into the Babylonian cuneiform? Now, first we have to express or convert this into base 60. Okay, remember our previous lesson on conversion from one base to another. We have to get 1,000. So that first we identify the powers of 60. 60 raised to 1 or 60 raised to 0 equal to 1. 60 raised to 1 is 60. 60 squared is 3,600. So this is already more than 1,000. So we have to begin with 60. Okay, so 1,000 divided by 60. Okay, what is it equal to? 1,000 divided by 60. Let's answer together. Divided by 60 is 16, correct? 16 remainder 40. Yes, 16 remainder 40. 16 remainder 40. Get the remainder 40 divided by 1, which is 4. Okay, so how shall we represent 10? So it is 16, 40, base 60. Yes? So 16, 40, base 60. So 40, how do we represent 40? 40 is now will be represented by how many wedges? 4 horizontal. 4 horizontal wedges. And how about 16? 1 horizontal wedge and 2 rows of vertical wedges. Okay, so this is how 1,000 is represented. Now you can verify. If you're not sure, then you can again multiply by the powers of Okay, you can multiply by the powers of 60 because it employs base 60. Now this one is 40. This is supposed to be 6 and this is 1 horizontal wedge. Okay, so this is 40 times 1 plus this is 16 times 60. Okay, 16 times 60 plus 16 times 60 is 6 carry 3, 960. Okay, 960 plus 40 is equal to 1000. Okay, so the answer here would be, so the answer to number 1, letter A rather, is 1 horizontal wedge with 3 or 2 rows of vertical wedges, 2 rows with 3 rather, vertical wedges, and then, okay, so this is for letter A. So I leave letter B, letter C, D, E, and F to you as your assignment. So part of your assignment. Number 2, letter A, because I'm going to leave letter B and C for your assignment. Okay, let's have this together. How many horizontal wedges are there? 1, 2, 3, 4. Okay, this is 46. Okay, and how about this? 46. And this is equal to 14. So the first set should be multiplied to 1 and the second set should be multiplied to 60. Okay, so converting this into our current number system, we'll have 14 times 60 times 60 plus 46 times 1. 14 times 60, what is it equal to? 840 plus 46, which is equal to 886. Okay, so it's equal to 886. So your letter B and letter C be part of the assignment. Now we move on to the next. The Rhind Mathematical Papyrus. So your Rhind Mathematical Papyrus was written by the scribe Amos, and it is one of the primary sources of Egyptian mathematics, primary sources of data or evidence rather of your Egyptian mathematics along with the Moscow Papyrus. It consists of 84 mathematical problems either relating to arithmetic or geometry. Now, the RMP or the Rhind Mathematical Papyrus was named after the one who purchased it in the name of Alexander Henry Rhind, a Scottish man. So it was named after him, Rhind. Okay, it dates back at about 1650 BC. It is a scroll. Okay, it's a scroll 12 to 13 inches wide and 18 feet long and written in hieratic script. The papyrus is now kept in British Museum. Now, what are the contents of the mathematical Rhind papyrus? The mathematical papyrus is divided into 3 parts. An arithmetical part, first is arithmetical, then geometrical, and the other is collection of miscellaneous problems. Now, determination of volumes, areas, time relation, line relation rather, are also contained in that book. Now, the section of the miscellaneous problems is interesting because it gives us some knowledge of Egyptian customs, their method of trading, of raising taxes, feeding animals, and of fixing comparative values of different foods and drinks by the amount that can be made from a unit of material. It contains also various methods of solution, some of which have come down to the present day and are found in our arithmetic. Okay, so three parts or three books. The first book is the book of arithmetic. Okay, the book of arithmetic whose contents are as follows: numbers 1 to 6, division of various numbers of loaves equally between two men, until numbers 39 to 40, division of loaves between men in an equal proportion. Book 2 of the RMP is about mensuration. Okay, and there are three parts of book 2. Part 1 is about volumes and cubic content in corn. Okay, part 2 is about areas, and part 3 about batter or angle of slope. Okay, the third part of the RMP is miscellaneous problems in arithmetic. Take note that it ends with problem number 84. So like what we said earlier, there are 84 problems in the Rhind mathematical papyrus, and for this session, we will look into some of them selected. So you might have encountered this already in the past about that puzzle. Okay, it's a classic problem, in fact, that appeared in the Rhind mathematical papyrus. And the puzzle or the problem goes this way. As I was going to St. Ives, I met a man with 7 wives. Every wife had 7 sacks. Every sack had 7 cats. Every cat had 7 kids. Kids, cats, sacks, and wives. How many were going to St. Ives? Says here, 7 houses, each with, 7 houses, each with 7 cats. But 7 cats, each with 7 mice, and each with 7 spelt, and each with 7 haircut. Okay, so houses, there are 7. With 7 houses, each with 7 cats, so 7 times 7, 49. Each cat with 7 mice, so 7 times 7 times 7, or 7 cubed, 343. Each cat with spelt. Okay, so 7 times 7 times 7 times 7, or 7 to the 4th. And each cat with spelt rather with haircut. The haircut is a unit of measurement in the ancient Egypt. So 49 plus 2, 343 plus 240 at 2,401 and 16,807. So in fact, sum of a geometric sequence. So it's a series. Yes, sum of geometric sequence. So the total can be calculated in this manner. 7 raised to 1, 7 to the second power, 7 to the third, and so on. Okay? Take note that when you speak of a geometric sequence, there is a common ratio. And that common ratio is 7. So, in fact, we could express it in terms of this. So, to get the sum, apply your concept of geometric series. Sum of a geometric sequence. So, it's a series. So 7 times 7 to the 5th minus 1 all over AR minus 1, or 19,607. Or manually, you can simply add up all of this. Okay, add this all up and you'll end up with the same answer. Okay, if we add this all up, we'll end up with, okay, so going back, 19,607. Some of the selected problems from the Rhind Papyrus are the following. Although we did this already when we tackled Egyptian arithmetic. And 2801 multiplied by 7. What did we say before? Multiplication in the ancient Egypt involves constant doubling. So 1 and 1, 2008. 1, double it, becomes 5,602. Double it, we'll have 11,204. And since our multiplier is 7, then okay, check for combination of numbers along the first column whose sum is 7. Okay, exactly. 1 plus 2 plus 3, 1 plus 2 plus 4 rather is equal to 7. Okay, so add this all up, the total will be 19,607. Another sample problem in the Rhind mathematical papyrus is this. Prove that 128 times 7 equals 2. Now let's look into the solution. So beginning with 1 and 7, so by halving. Okay, by halving, if you get half of 1, that's 1 half. Yes? And if you get half of 7, that will be 3 and 1 half. So halving. So first step is by halving. And then take also the half. Okay. Having, yes, 1 half. Take half of 1 half, that's 1/4. Okay, 1 half. Okay, 1 half of 1 half is 1/4. 1 half of 3 is 1 and 1 half. And 1 half of 1 half is 1/4. Okay, next. Now we get unit fraction. 1/7 from here. 1/7 of 7 is 1. Okay, 1/7 of 7 is 1. Next, half it. Half of 1/7 is 1/14. 1/14. And half of 1 is 1 half. Okay, half of 1 is again 1 half of 1/7 is 1/14. 1 half of 1 is 1 half. Now let's continue getting the half. Half of 1/14 is 1/28. And half of 1 half is 1/4. So look for along the second column, look for a combination of numbers whose sum is 2. And where is it? Sum is 2. Sum is 2. Ayan. This plus 1/4. Okay? Because 1 and 1 half and 1/4 plus 1/4 is equal to 1 and 1 half plus 1 half. Yes? Which is equal to 2. Okay? So, correct. So, we were able to show that 1/4 128 times 7 is equal to 2. There. We have here 1/4 and 1/28. So that's from the RMP. Next, another problem that comes in the RMP is this. Divide 3 by 10. So just the same, get 1 and 10 and then start by unit. We take unit, 1/10 is equal to 1. And then we double. So here, unit, take the unit fraction. And then here, we double. Okay, or twice. Twice of 2/10. Twice of 1/10 rather is 2/10, which is 1/5. Yes? And twice of 1 is equal to 2. What are we looking for? 3. Okay, a combi of numbers whose sum is 3. So what are they? This. Okay, 2 plus 1 is equal to 3. So answers are 1/10 and 1/5. Okay, that's it. So for your task, I want you to watch this video about Plimpton 322 and answer the following questions. Number 1. What is Plimpton 32? 2. What does it reveal about ancient Babylonian mathematics, and what is the advantage of using base 60 over base 10? All these questions could be answered from the video. So I want you to watch intently the video, and it's only for 2 minutes. Bye everyone.